x cubed is 3x squared. And that's the way they did it in class. So let's do that just to be sure. So if u is x cubed, then the derivative of u is 3x squared. And I write the dx after it. Well, if x is the variable, the derivative of x is 1. So to me, this is just like writing 1 there. That's how I view the dx. Now it's just a game to try to change this whole thing into u. So I'm going to do it real slow this one time. 5x squared for u. And I've still got a dx. Okay, I see the x squared and I see the dx, and I see how to isolate that here by doing 1/3 du is x squared dx. So now I can replace these two. I'm going to pull the 5 out front. I'm going to just write it like this. Right. You don't need to show all these steps, but I will this time. Pull the 5 out front, reorder what's on the inside. So that's 5 integral 4 to the u. We figured out that's 1/3 du. So now the whole thing's 5/3 integral of 4 to the u du. Questions any of those steps? Well, now this is one we're just supposed to have memorized or be able to guess. And it's just a matter of remembering if y is 4 to the x, then y prime is 4 to the x ln of 4, which means when I take the derivative of 4 to the x, I get a 4 to the x ln of 4. Well, then if I take the antiderivative of this, I need the opposite of that. So that's going to be 5/4, 1 over ln of 4, 4 to the u, plus a constant. Because if I take the derivative of this, I'll get 4 to the u times ln of 4, which will cancel. And I'm done as soon as I put it back in terms of x. So 5 over 4 ln of, why did that turn into a 4? That was bizarre. Effective marker, I'm going to change it. Something wrong with that marker. And what was u? X cubed. Right, we're done. Good. That went on the board the other day. Questions about it? Mm-hmm.
How did the natural log get on the bottom?
The natural log get on the bottom because, let's just do a different problem. Let's say 3 to the x dx. What's the antiderivative? I'm going to make a guess. My first guess is y is 3 to the x. Because like e to the x derivative is e to the x, right? Okay, take the derivative. Y prime is 3 to the x times the natural log of 3. That's the derivative of 3 to the x. Now, that wasn't what I wanted. I didn't want a natural log of 3, did I? So my next guess should be y equals 1 over the natural log of 3 times 3 to the x, because that's just a number, right? So when I take the derivative of it, Cody, I get that number times the derivative of this, which is 3 to the x times natural log of 3. They cancel. I threw it on the bottom, just like I threw the 5 out front, just like I put the 1/3, because that, well, no. But it just, I'm adjusting for the constant. I'm making it go away because I don't want that when I take the derivative. We could check our derivative here. Our derivative, if this is y, then y prime is, that's all a constant. Then the derivative of this is 4 to the x cubed times the derivative times ln of 4. That's the derivative of 4 to the x part, times the derivative of what's up top. Now let's see if we got it right. The 3 cancels, the ln 4 cancels, and sure enough I have 5x squared 4 to the x cubed. So I know my answer is right because I just took the derivative. Go through your next test, you get time at the end, go back, take the derivative of all the antiderivatives, be sure you got them right. Okay. But Andrea's question was, how do you pick the u? Well, suppose I pick the u as 4 to the x cubed. Then du would be 4 to the x cubed times ln of 4 times 3x squared, right? dx. Right, suppose that's the u I picked, 4 to the x cubed. And here's my du. 4 to the x cubed, ln 4 times the square root of that, dx. Alright, what's my integral become? My integral, which was 5x squared 4 to the x cubed dx. Okay, let's see, I've got an x squared and a dx. So if we isolate the x squared and the dx, well, actually, we've got an x squared and a 4 to the x cubed, don't we? Let's do this the smart way. Let's isolate all of it. See, if I just throw the ln 4 and the 1 over ln of 4 times 3 times du, move this and that over the other side, then I've got the whole inside, don't I? What are you doing? See what I did? Well, wow, that's the whole inside. So this becomes 5 integral 1 over ln of 4 times 3 times du. What do I do with that? Those are all constants. Pull them all outside. Okay, what's the antiderivative of du? The antiderivative of 1. Just u. What's u? What's that? I hope it's the same thing we got over there.
Yeah.
It is. So there are incorrect u's. What's the moral? The moral is, yeah, you can pick the wrong u. Go ahead, pick that for you and see how far it gets you. But you'll know immediately when you start doing it that you're going nowhere if you pick the wrong u. But there are often lots of correct u's that work. There are often lots of correct u's that work. So you could pick u as the whole thing, or you could pick u as that. Just pick something and go if you think it's a u substitution. Okay, question on that. Does that help with u substitution? Help with that's supposed to help with two things. One, it's supposed to help you with these nasty exponential functions, and they are nasty. You know, it's, I remember being scared of them when I was a student, but they're not really that hard. And u substitution, I remember thinking, well, how many different ways can you do it? Answer, more ways you can possibly imagine. I'll give you one integral in a couple of weeks where I'll ask you to do it 4 different ways. Okay. So now I want to talk a little bit about Scorpio's problem, because some of the problems I put in here for a reason. People often struggle with the du dx, the notation here. Like we went from u equals x cubed, and some people will write this, du dx is 3x squared, and then multiply across by the dx. Physicists, engineers, mathematicians have been making use of this notation for years. But it's very misleading, because in this case, this is some function. It's not a fraction, it's the function which is 3x squared. Well, if I wrote f of x is 3x squared, you wouldn't be happy if I wrote that. Take the bottom half of the function, multiply it across. And this is one function. It's not two different things. Right, I took half, divided the function in half, and put the top here and the bottom over there. He didn't like that. Why would you like it me taking this function and taking it apart? Well, you shouldn't like it. And we are using this notation in very, very many different ways. And I consider it pretty much a disservice to the students. And if I wrote my own calculus book, I wouldn't use the notation at all. But many of you are going to see it as engineers. And so I'm going to stay with the notation even if I dislike it. But I will make it make sense to you in at least one example here. And that was a point of 212 at Scorpio. Substitution, use substitution. You'll later on in engineering courses and upper level mathematics courses, you'll see something called change of variables. It would be much better if we called this change of variables, because what we're doing is we're replacing we're writing a relationship between two different variables. And so for this problem, for example, if you wrote it out like you should with the variable showing u of x is 2x cubed plus 10, then u prime of x would be 6x squared. There wouldn't be any magic, no dx's, no du's anywhere. And we could rewrite this integral as the integral of, let's see, using the hero notation, 1/6 u prime of x equals x squared, right? We could write this as 1/6 u prime of x times u of x to the 15th dx. Which I could rewrite as 1/6 integral of u of x to the 15th power times u prime of x dx. Now, you know your chain rule. What's that the derivative of? What happens when you take the derivative of something to a power? Well, the power goes out front, this stays on the inside, you decrease the power, and then you multiply by the derivative, right? So the antiderivative of this, or this is the derivative of 1/16 u of x to the 16th, right? You take this, 1/16 times 16, that's 1 times u of x to the 15th times u prime of x. You get that back. So you can make it precise and write the variables out. And then you realize, well, wait a minute, I knew what that was. That's 96, and u of x is 2x cubed plus 10 to the 15th plus k. Well, that's the same answer you would have gotten when you did it with u substitution. So u substitution can be made precise, 1. 2, it really should be called change of variables. Okay, questions, anything there?
Can you always do it like that? That makes a lot more sense.
Let me make clear, when I write these problems on the test, I may give you a hint, try u equals or something if it's a challenging problem, but I won't restrict you to how you do the problems. If you write valid mathematics like this, that's fine with me. I will say, however, that there are problems. I'll make up one here. Where rewriting it accurately using that, well, this may not be one. I can come up with some where it's really tricky to do. But the answer is you can do all of them this way. Yes, u substitution can be made precise by writing the function and the variables completely out, and it does make much more sense to me to do this way than to do the u and to break up the du and the dx. But some of them are quite challenging. Yeah, Mark.
If you had a problem with 3 variables, could you still use u substitution?
When you have multiple variables, when you take Cal 3, you will. You do something, they don't call it u substitution, they call it change of variables. And so, yes, when you have integrals like the integral of x minus y over 2x plus y dx dy. So this is a function of an integral with multiple variables in it, which you'll see there. Sometimes you'll let u equals 2x plus y and v equal x minus y, and now you just have the integral of u over v. But what goes out here? What is the du and the dv? Well, that's more complicated. It's not just du dv. So yes, we do change the variables. Well, you'll see them in Cal 3. They'll have multiple variables in them, and that's why I think it's worth knowing that this is a change of variables. So when you see it in Cal 3, it doesn't look like something totally unrelated. U substitution was one magic. This is some other magic. No, it's all the same magic. It's all change of variables. And it can all be made precise by writing out the function carefully, although it can be hard to do.